Hey everybody, here with our fourth installment of logistic regression. In this video, we'll take a look at situations with multiple predictors and some issues around that, and we'll get to kind of a detailed example that we'll use in this video and in the next. Using multiple predictors, we're going to use, again, the same data set that is focused on compliance with mammography screening recommendations. And we have a number of predictors in here, but I'm just going to show how we can add a second predictor as a quick multiple predictor example. Here we're predicting compliance with screening recommendations, that is whether they got screened or not, just a yes or no response. We're going to predict it from physician's recommendation again, which we looked at in the last video, but we're also going to add in knowledge. And we can just keep adding variables here, just like we did with linear regression, pretty much the same concept. Remember the big difference here between linear regression and logistic regression is that we're predicting a dichotomous outcome, that is an outcome that is a yes or a no. And when we do that, we have to tell R that we're using a binomial function. And that's where we get this family equals binomial. The command here is GLM rather than LM, but otherwise looks very much the same. So what we see here is physician's recommendation remains significant. We can see that with the estimate. Remember, those estimates are log odds ratios, not odds ratios. The log odds ratios have positive and negative values. Positive means there's a positive relationship. Negative means there's a negative relationship. But they're not particularly interpretable as is, which is why we'll end up converting them when we converting them to odds ratios when we want to do some sort of interpretation. Physician's recommendation is significant. Knowledge turns out wasn't significant, didn't improve prediction. Also in this output, we see the null deviance and residual deviance. Again, we saw last time, if we take the difference between those two values, it gives us a test of significance for the entire model. That is, did the variables in the model together significantly predict compliance? We won't take a look at that here, but we'll take a look at that in a more detailed example later on. Similarly, as we did with regression, with linear regression, that is, we can use interactions with logistic regression. Here's an example where we're predicting compliance, not only from physician's recommendation and knowledge, but from the interaction of the two. And we can see when we did that, well, nothing comes out significant. And that brings up an issue that we should talk about again, and that is centering. Physician's recommendation went from being significant to non-significant. That seems a little strange. One of the issues that we'll see is that when we don't center our variables, it'll cause problems for getting a good estimate of what the effects actually are. So here's an analysis that's uncentered, very easy to forget, and just to simply throw stuff in and uncenter, and you'll get very, very strange findings when you compare it to a centered analysis. In this next slide, I'm going to take a look at what happens when we actually center the variables. Let me get myself out of the way there. When we actually center the variables, the relationship ends up shifting quite drastically. And we'll see here that now we have a significant effect for physician's recommendation again, but knowledge and the interaction remain non-significant. In fact, the interaction is exactly the same as it was before, and you'll see that with centered versus uncentered. Again, the issue that we have here, and we saw this issue earlier in the semester, is that if we multiply variables together to create an interaction term, that produces a lot of what's called non-essential multicollinearity. The basic issue there is that you've got physician's recommendation and knowledge, and they have strong correlations with the interaction term, and we'll take a look at that in a second. The reason why they have strong correlations there is because the interaction is a product of those two. When we center our variables, we actually can reduce that multicollinearity quite substantially. So taking a look at a little bit more on centering, what I did here is I created a couple of sets of variables. I created an interaction based on the left-hand side, based on the uncentered variables. And then on the right-hand side, I centered all of the variables. One thing to to note here is physician's recommendation was a yes/no question. I had to convert that to a numeric variable in order to center it. It'll throw an error at you if you try to center a categorical variable. So that's one consideration there if you're trying to do this yourself. Looking at the uncentered variables, I've got the correlations between the predictors and the interaction. If you see on the bottom, physician's recommendation and knowledge both have relatively substantial correlations with the interaction. In particular, physician's recommendation is almost 0.89. It's a pretty gigantic correlation. However, simply centering the variables, that is, centering them on their mean, which means that we're taking each variable, subtracting it from it, the mean value, which means that your new mean is now 0, dramatically reduces that non-essential multicollinearity. Now you can see the correlations are much smaller, 0.06, 0.027. So it really does make a big difference. Remember that multicollinearity, when those numbers start to get high like this, they're going to create problems such as inflated standard errors. The upshot of it is you're going to start having problems detecting significant effects when there are actually effects there, as we saw in the previous example. All right, here is an example that we're going to use for the rest of this video and for the next. And this is the example that appears in your handout and in the logistic regression handout in some detail as well. Here is a model predicting compliance from doctor's recommendation and knowledge, as we saw before, and we're going to add in 2 more variables: perceived benefits and perceived barriers, I should say. So taking it from the top, the first thing that I would look at would be the model statistics, or the first thing I would talk about would be the model statistics and reporting. So I've got a chi-square here with 4 degrees of freedom. Those 4 degrees of freedom, you get 1 for each predictor variable, basically. You can see down at the bottom, I've calculated that 58.78 or 58.8. That's just the difference between the null deviance value of 226.47 and the residual deviance, or the model value, of 0.167.7. And again, you can see the difference between the degrees of freedom there is 4. That's reflecting the difference between the 2 models. Remember that null model is basically a model that has no predictors in it. That is, how well could we predict compliance if we didn't have any predictors? And this is how, and the residual deviance is how well we're predicting if we have all 4 of these predictors in the model. The difference between those 2 values gives us a statistic that's very much like the F model statistic in linear regression. It tells us whether our variables together significantly predict the outcome. In this case, we have a significant chi-square value, so we can say that the model predicting compliance was significant. Compliance from these 4 variables was significant. Just like with regular linear regression, just because a model is significant doesn't mean that every single variable in that model is significant. So then we move to the coefficients. I generally present what's called the exponentiated B. That is the odds ratio. People don't write it as odds ratio usually. Exponentiated B is, I think, the most standard notation. The exponentiated B is our coefficient in terms of odds rather than log odds, because none of us actually think in log, or maybe some of you think in log terms, but not many people do. So physician's recommendation was significant. We can see that it's got an odds ratio of 6.31. So that means holding all of these other variables steady. Physician's recommendation, if you have one, you're 6.3 times have 6.3 times higher odds to get comply with recommendations. Knowledge is non-significant here. We can see that the odds there are hovering right around 1. Odds around 1 would mean that knowledge doesn't make any difference. Benefits has odds greater than 1. Remember the rule here with interpreting odds: if it's greater than 1, it's a positive relationship. If it's less than 1, it's a negative relationship. Benefits was significant, and what this means is those who perceive more benefit are more likely to comply with mammography screening. Then barriers. Barriers had a value of 0.056 for its odds. That means that as people perceive more barriers, they had less. They were less likely to comply with recommendations. So if you thought it was going to be difficult or painful or a whole host of other issues, that you're probably less likely to comply with getting mammography screening. So again, very much like with linear regression, we want to talk about the model first. Okay, was the model significant? In most cases, we're going to find a significant model. Then we're going to want to pick through, talk about which of the specific variables in the model were significant. And then finally, as the last step, we're going to explain it in plain English. The plain English explanation I have here: those who received a recommendation perceived more benefit, and fewer variables were more likely to comply with recommendations. Just something of that nature. Again, the plain English explanations are really important because those really get at being able to explain things to people who maybe don't understand logistic regression or don't understand statistics in general. All right. Taking this example a little further, we can look at classification for the four predictors. Chi-square is a nice test, a significance test for how well our model fit. Classification, to me, though, seems a little more little easier to interpret, gives you a better sense of how well you are predicting people. Now, to start off with, in the previous video, we talked about kind of a baseline for prediction, and that was a recognition that if you don't know anything, you could always predict the most common outcome. Here, the most common outcome was not getting screened. 54% of the total sample didn't get screened. So if we predicted everybody as not getting screened, we'd be guaranteed to get at least 54% correct. So that's kind of our baseline for prediction when we're talking about classification. So taking a look at the classification table, again, how you read this, we want to match up the zeros with the false and the 1 with the true in this case. What that's going to give us on the upper left and lower right diagonal, those are the people who are correctly classified. Those 60 people, they were actually zeros, which was a no. They didn't get screened, and we were predicting that they were not, and our prediction was that they wouldn't get screened. In the lower right-hand corner, people who actually got screened and were predicted to get screened, so we got 53 of those correct. In addition to that, we have 51 incorrect classifications. That would be the people who we predicted to get screened, but were actually zeros, indicating they didn't. And the people who we predicted would get screened, but actually had not gotten screened. So in total, this gives us 69% correct, and that's just 60 plus 53, the correct ones over the total of 164. So we went from getting from a baseline of 54 correct to 69% correct, so almost 70% correct from a little bit over 50% correct. So it gives us, I think, kind of a nice common sense way to understand the quality of our prediction. All right, the next slide we'll talk about some other useful statistics.